All right, let's get into Chapter 5, IPv4 and IPv6 addresses. We're going to go over binary again just as a refresher, IPv4 and IPv6 addressing, as well as how IPv4 addresses are assigned, and we're going to talk about subnetting. In class, we will go over many different kinds of subnetting problems and how they might appear on the test. So let's talk about binary. We grow up using this base 10 system that we have now, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But computers and networks don't understand decimal numbers, they only understand binary. So they relate to just ones and zeros, or the base 2 system. So basically something is on or it's off, or it's yes or it's no. And the binary conversion table looks like this. So within an IPv4 address, you have 8 bits in each octet. And when we're converting back and forth between, we put our ones and zeros in this kind of table to convert back and forth. So we'll see examples of that in just a second. So the minimum amount that can be put in this table is everything is 0. The maximum amount is everything is 1. And when we convert that over to decimal, that shows up as 255. When we convert from binary to decimal, you get your ones and zeros already in place, you set them up in this table, and then you add up all the places where you see a 1. So in this case, we have 128 has a 1 in it, so we'll add the value 128. So does 16, so we'll add 16. The 4 and the 2, so 128 plus 16 plus 4 plus 2 equals 150. So what you see here is the binary equivalent of 150 in decimal. When you're converting from decimal to binary, there's a little bit more of a process to it. Essentially, you're starting with a decimal number, and then you're trying to fill in this chart. So, to do that, is 167 greater than or equal to 128? And it is. If it is, then you put a 1 in the column, and you subtract that 128 from 167. You get a remainder of 39. Then you repeat the process going all the way through the table. Is 39 greater than 64? In this case, it's not, so we're going to put a 0 in the 64 column. We're still working with 39 because we didn't fill anything in here. So is 39 greater than or equal to 32? It is, so we put a 1 in that column. We subtract 32 from 39. That gives us a remainder of 7. We move to the next column. Is 7 greater than or equal to 16? It's not, so we put a 0 there. We go on. Is 7 greater than 8? It's not. We put a 0 there and go on. Is 7 greater than or equal to 4? It is, so we put a 1 there. We subtract the 4 from 7, and we get a remainder of 3. Is 3 greater than 2? It is, so we put a 1 in the 2 column. We subtract 2 from 3, we get 1. And 1 is equal to 1, so we put a 1 there as well. We can check that by going back, and everywhere we have a 1, adding those values together, and we get back to 167, our original number. So that's how you convert from decimal to binary. So an IPv4 address is a 32-bit address. We get that 32-bit because each one of these octets represents 8 bits, and there's 4 of them. 8 times 4 is 32. It's typically written in what we call dotted decimal notation. So when we say an IPv4 address, we pronounce it as 10.1.2.3. So we have 4 separate numbers separated by dots. Again, we call each one of those an octet because it represents 8 bits of information. When we refer to 8 bits of storage on a disk or a flash drive, sometimes you hear that referred to as a byte of information. So here's the structure of an IPv4 address. So if we took the 10.1.2.3 and we converted them to binary, this is what it would look like. And we would refer to these as the first octet, the second octet, the third octet, and the fourth octet. The subnet mask identifies how the network is divided. So we use subnet mask bits to indicate where this network information is. So when you see a 1 in a when you see a 1 in a subnet mask, it contains network information. When you see a 0, it pertains to host information, and we'll go through examples of this. So here we have the IP address in binary. We add the subnet mask in decimal. In this case, it's 255.0.0.0. Then we see the binary equivalent of those, and we can see that where we have the ones is within the first octet, so those represent the network bits. Everywhere else we see a 0, so that represents the host. There are 5 different classes of IPv4 addresses, and you need to know where these classes are for the purposes of the test. So there's a little memorization here. Class A, B, C, D, and E. Now D and E you generally don't subnet with. D is used for multicasting, and E is used for research and educational purposes. So we don't really see those on the test. Now you might be asked to be given an IP address and say, what class of address would this fall in? And that's when you would need this information. So a class A, the value in the first octet, is either 1 up to 126. Remember, the value in the first octet determines the class. That's it. Just the value in the first octet. The class full mask, or the unsubnetted subnet mask, for a class A address is 255.0.0.0. And the prefix notation, or the CIDR, as it's sometimes called, is a /8. So all that means is 8 bits are turned on. They're the first 8 bits, and so oftentimes you will see a class A address and it will have a /8 behind it. That just means that that's what the subnet mask is. A class B address goes from 128 to 191, and the class full mask for that is 255.255.0.0. Those 2 sets of 8 bits turned on, that means that the CIDR, the prefix notation, is a /16. For class C, we've got 192 to 223. The mask for that, 255.255.255.0. Since 3 sets of 8 bits are turned on, 3 times that, 8 is /24, so that makes that our prefix notation. Then we've got class D, 224 to 239, and class E, 240 to 255. Then we have the private IP network ranges. We've got private address ranges for class A, B, and C. Class A is anything that starts with a 10, so it's the easiest one to remember. And again, the default subnet mask for that is just going to be 255.0.0.0. Then the Class B address is anything that starts with 172.16 up to 172.31, and the default subnet mask for that is 255.255.0.0. A Class C address starts with 192.168 something. Anything else in the last 2 octets, as long as it starts with those first 2, it's a Class C address. Class C private address. Default subnet mask for that is 255.255.255.0, and those are our private IP networks. There's a couple of other special address ranges that are worth noting. The first one is a loopback address. So it's technically a Class A address because of the fact that it starts with 127. Generally, we see the loopback listed as 127.0.0.1, but in reality, it can be anything in that 127 range. The default subnet mask for that is 255.0.0.0. And this is normally when you want a device to ping itself or communicate with itself. It's like a test of the IP stack. You would ping the loopback address, and you could pull up and do that in command prompt just to ensure that your computer can send and receive packets. The last one of these is called a PIPA. So a PIPA stands for Automatic Private IP Addressing. So this is a Class B address, and it's anything in the 169.254 range. So essentially what this is when you get an IP address, you're normally going to get it from a DHCP server, but if for some reason that fails, what you'll see is a pip address pop up. So those are the operating system is assigning that to you when it cannot get in touch with the DHCP server for whatever reason. Anything from the cables unplugged to the servers down to the router has stopped working. You get a pip address. So very commonly one of the troubleshooting scenarios that you would see would be that you're not able to connect to the internet at any capacity. What's the next step you should do? And that would be to pull up command prompt and do an ipconfig, which we'll talk more about later on. Just pull up ipconfig and see if you actually have a valid IP address or if you have an address that starts with 169.254, in which case you have a pip address and you're not getting anywhere on the network, outside of the network, because you don't have a proper IP address. So in the address structure, looking at where these 255s or where these ones lie that give us the network information in a Class A address, if we're using this classful subnet mask, we have all the ones in the first octet, which means that that's the octet that has the network information in it, and everything else contains the host information. For a Class B address, the first 2 octets have our network information. They're the ones with the ones in them. And the last 2 have the host information. In a Class C network, we have 3 octets that are full of ones, so the first 3 octets are the network information, and the 4th octet is for the host. We have 3 categories of IPv4 addresses: unicast, broadcast, and multicast. Let's talk about what each one of those does. Unicast traffic goes from a single source to a single destination. So in this instance, we've got a couple different packets that are moving across the network. 10.1.1.1 is a destination. Here's another one, 10.1.1.2. So those packets are going from one place to another place, just one sender, one receiver. Then we have a broadcast. A broadcast goes from a single source to every single device on the network. And you can tell that it's a broadcast packet because it uses this broadcast address, which is all 255s. We also have a multicast type of address. So this, we'll talk more about this in later chapters, but you can see the multicast group is within that Class D network that we just talked about. So the traffic travels from a single source to multiple but specific devices on the network. So typically these 2 receivers over here are going to opt in to be part of this multicast and get this information. So let's say someone is streaming a meeting or a conference or some kind of training, and it only needs to go to these 2 receivers, but it doesn't need to go to this one. So they will opt into this multicast traffic so that they're able to receive it. It's specialized and it's not used as often as the other 2. Components of an IP address: we've got the IP address, the subnet mask, the default gateway, which is the IP address for the router or the thing that gets us out of the subnet or out of the network. Then we've got some server addresses like the DNS server or the WINS server. The the WINS is primitive DNS, so we don't see it used very often, and sometimes it might even be disabled. We can statically configure our IP addresses. It's very easy to do. It's a simple process, but it is time consuming, and people tend to fat finger and type in addresses incorrectly. And on a very large network, it would be difficult to go to every single computer and put in a static IP address. So to combat that, we use what's called dynamic configuration. So in the beginning, we have what was called boot P. It's generally considered to be obsolete now. Now we use DHCP. So it assigns an IP address, a subnet mask, a default gateway, maybe even DNS server information, or if there are any variables that are related to a VoIP, a voice over IP system, DHCP will give those things to the client machines that need them and keep track of who has what for however long they need it, and it will all be done automatically. Again, just a word on a PIPA. A PIPA is when a device doesn't have something static programmed already, and it's not able to contact the DHCP server. So again, when you see this 169.254.0.0, and the subnet mask would be 255.255.0.0, that means that it cannot get on the network. They refer to this as what's called a link local address, which essentially means it's not getting off the local link. It's not getting to another subnet or to another network, to the internet. It's only going to be able to operate locally within that LAN or within that subnet. So subnetting, everybody's favorite subject. So the default classful subnet masks are not generally what we want when it comes to subnet size. For example, a Class A address has over 16 million possible addresses. That's really one giant network. We want to modify that so that we can create smaller chunks of network. We're going to borrow bits from the host portion and add them to the network portion so we can have more networks. So the purpose of subnetting is to make more efficient use of IP addresses, separate off our networks for security, and we can maybe give certain bandwidth restrictions to one subnet over another, or not throttle bandwidth on one part of the network but do it on the other. So here's again our classful subnet masks and what those assignable IP addresses look like. But that's a lot of networks, right? It's a lot of hosts, I should say. So here we have our subnet mask notation. And you can see the prefix notations that go along with them here. The ones that are in red are going to be the classful ones. Prefix notation, slash notation, CIDR. But this number refers to the number of bits turned on in the subnet mask. That's always contiguous, one right after another, going from left to right. The subnetting formulas you absolutely need to know. You can get a tattoo of them if you like, but I won't give you extra credit. But you can calculate the number of needed subnets by knowing these two formulas. They will get you very far when it comes to any kind of subnetting on any kind of exam. So you have the number of created subnets, which we call 2 to the S. S is the number of borrowed bits. For the number of assignable IP addresses, we have 2 to the H minus 2. H is the number of host bits. We have minus 2 because we cannot use the network and we cannot use the broadcast address for every single subnet that we create. So this gives us the number of assignable IP addresses. If we wanted the number of total IP addresses, we just wouldn't subtract this 2. So pay attention when you're reading questions on the exams. Do they want the total IP addresses or do they want the assignable IP addresses? Because the number will be different. So if we want to look at the number of created subnets, in this example they've given us a Class C address. Normally this would be a /24, but in this case they've made it a /26. So they borrowed 2 bits from where the host should be. Normally you would have 8 host bits. Now they took 2 of those away when they made this /26. They put it on the network side. So they borrowed 2 bits. If we want to find the number of networks that creates, or the number of subnets, we would plug that 2 into this S here. That gives us 2 to the second. That equals 4. That means we just created 4 subnets. When we talk about assignable IP addresses, we get the same equation here, so to speak. We have a /26. The total bits are 32. This is a /26. 32 minus 26 means there's 6 host bits left. So there would be 2 bits taken up right here and then 6 bits that are zeros. When we add this in the equation, 2 to the 6th minus 2 gives us 64. Then we subtract, 2 to the 6th gives us 64. We subtract 2, we get 62. So 2 to the 6th minus 2 is 62, which means there are 62 assignable IP addresses on each subnet. So we have 4 subnets, each with 62 assignable IP addresses. If we look at how this comes out, we have a /26 right here. We're going to increment by 64. So to do that, we're counting where does this last one fall. We'll do many examples of this in class. And we're going to subnet by that number. We call it the increment. So if I subnet, I end up with a 0, 64, 128, 192. And after that, I go over 255. So it's no longer valid. The broadcast address, remember, is going to be one less than the subnet address of the next subnet. That makes us a /64. And from then, we're adding 1 to the subnet address to get the first usable IP, and we're subtracting 1 from the broadcast address to get the last usable IP. And we will do that all the way through the range, and that's what this would look like. CIDR is also used to summarize networks. We call this route aggregation. You really just need to know what route aggregation is, but you can advertise multiple individual routes as a single route, kind of like this shows. So basically what this says is all these networks have the first 22 bits in common. So these are the first 22 bits, they're outlined in red. After here, they start changing. So we're just going to summarize these routes and call them 192.168.32.0, which is how it starts up here in the network address, /22, because the first 22 bits are the same. That's really all you need to know about route summarization at this point. You'll get more into it in your Cisco studies. So everything was great in the world of IPv4 addressing, but then we kind of sort of ran out of addresses. So you saw that we had millions and millions and millions of addresses available, but everything became wireless, everything became networked. I mean, our refrigerators get on the internet at this point, so we've run out of IP addresses. So what they did to fix that was to bring up this IPv6 addressing, because it gives us much, much more options when it comes to providing IP addresses. So here's what this looks like. With IPv4, we had 2 to the 32 because there's 32 bits in IP address. So we had 4.2 billion addresses. We used that up pretty quickly, I think sometime in the 90s. With IPv6, instead of having 32-bit IP addresses, we have 128 bits to work with. That gives us 340 undecillion addresses, which is a lot. So we've increased our address space by many, many times. Some changes to IPv6. There are no broadcasts. There's no fragmentation of packets. You can work with IPv4 as well as IPv6 while we're transitioning between the two, and the packets look a little bit more simpler. So if you look at IPv4 versus 6, you see we need more space because we have a much larger source and destination IP address, but they've gotten rid of a lot of the headers and stuff that happened here, or they've condensed them down and made them a little bit more efficient. The structure of an IPv6 address. So a full IPv6 address looks like what you see here in the middle. So it's hexadecimal. It has 4 characters in each hextet, and there are 8 hextets. So you can see 1, 2, 3, 4, 5, 6, 7, 8 hextets with 4 characters in each one. Now we also can abbreviate these addresses. So the rules on abbreviating addresses is you can get rid of a leading 0. So in this case, 0, 1, 2, 3. This 0 is leading, so it's kind of, it's extra. If you look here at 4040, that's what we call a trailing 0. You can't change a trailing 0. You can't take it away because then it changes what this whole hextet means. Another thing that you can do is if you have multiple groups of zeros, you can condense that down into just what's a double colon, but you can only do that one time. So when I look at this IPv6 address, I can see 1, 2, 3, 4, 5 hextets are represented. I know there's 8 total hextets, so that means 3 of them have been turned into contiguous zeros right here. So you can come back up with what the full IP address was. There's 3 different types of IPv6 data flows: unicast, multicast, and anycast. An IPv6 unicast, just like an IPv4 unicast, is the traffic that travels from a single source to a single destination. And you can see here we've got : 2, : 3. They've simplified these just for us to be able to see them. But a single source, a single destination, the addresses just look a little bit different. With an IPv6 multicast, from one single source to multiple but specific devices on a network, just like multicast and IPv6, of course the addresses are different, including what multicast looks like in IPv6, which is represented right here. Then we have the IPv6 Anycast. So this is a new and different thing. This is essentially going from a single source to the nearest device on the network. So it may pick between different routers, which ones are close, which ones are more available, which ones have more speed associated with them, but this is meant to be more efficient. This is a more efficient way of dealing with packets in IPv6.